won't be that smooth. So your journey will be very smooth, right? So that's how in cheap solutions, low-cost solutions, generally BLDC is used, like those low-end two-wheelers, electric three-wheelers. These are very cost-sensitive segment. So there people go with cheaper solution. But in a four-wheelers, you're spending lakhs of amount, right? High-performance two-wheelers, you're spending lakhs. So there, a few thousand here and there won't make much difference, but you would like to have better performance. So there, generally, people go with PMSM, okay? Let me quickly see if you have any questions. What is generally regenerative recharge amount in one braking as compared to battery? So regenerative braking in total in overall one complete cycle, right? That is typically hardly 5 to 10%. And in one braking, it will be, I don't know, it may be 0.4, 0.5, 0.1, depending on what was the speed of the vehicle at that point of time, right? How much ratio of mechanical and electrical braking was given a speed. So a lot of complicated things, but generally regenerative braking don't give much benefit to contrary to regular claims. Okay, typically overall entire one drive cycle or one full cycle, it can be hardly typically 5 to 10%. And that itself is good for several vehicles, of course. There is another question: if more number of turns, I think in the motor you're talking about, then will it give more rotational power? More number of turns, basically you see it helps in the EMF part, right? Yes, more number of turns, sometimes it helps, but it has its own size limitations also. You cannot have infinite number of turns. That is true. Okay, there is a question: is back EMF and EMF exist in same time in a motor during degenerative braking? Okay, so yeah, let me discuss why it is called back EMF. That I missed. I would have told it in the next class, but then it's okay. So now, this EMF versus back EMF, what is the difference? So EMF is a terminology, we are going to use it in the generator. Generator, what happens? We give, again, I'm repeatedly mechanical input, we get electrical output. So what we generate is basically EMF, voltage, right, in simple terms. But in motor, what happens? This is my motor, okay? So in motor, we already give electric supply from some sources, right? Some sinusoidal sources, let's say. Now, inside the machine, we already have the coils, right? So we give power supply to the coils directly, right? And as a result, it creates a rotation in the motor. How it creates, I'll talk about it. Simple. Just give me a minute. Well, let's first talk about how we create torque. Then I'll address this question. So let me take 2-3 pages here quickly. That's a very important question. So first, let's understand how do we create torque in a motor, or in general, how motor works. So for motor to work, it must produce torque. Question is how. So in motor generally, there are two broad categories of torques production technique. One is called electromagnetic. Generally, another is reluctance-based torque. Okay. For example, the torque in SRM, SYRM. Electromagnetic torque example could be your induction machine, PMSM, BLDC, induction machine. They will also have a little bit of additional reluctance torque. Okay, but majorly it will be electromagnetic torque. Now, what is electromagnetic torque? First thing is, let's understand simple torque production through magnet. So let us assume that we have a magnet NS, permanent magnet, okay? PM. Remember, what is PM? Permanent magnet. Simple. Let us assume that this permanent magnet is on a rotor, so it can rotate. Okay? We have made an arrangement like this. So maybe there is a rotor and we put magnet on it, so it can rotate if you give rotation. Now, somehow, if I create a magnet here, and I create a south pole here, what will happen? This will try to rotate and align across this, isn't it? Because we know opposite poles attract each other. Simple. So from initial position 1, it will go to position 2. What if, when it reaches position 2, what if we also rotate it somehow? Cancelling this, I created another S pole here. So now this will rotate to this position 3. I hope you're getting the idea, right? So conceptually, it is something like this. I had a beautiful picture to explain that. Yeah, so the picture is something like this. So imagine that you have a donkey, right? And you're putting a carrot in front of it somehow, right? This arrangement. So donkey thinks that if it moves a little bit, it will be able to eat the carrot. But as soon as donkey moves, carrot also moves further, right? And this goes on. So similar concept here. The rotor, when you created a S pole in the stator, it moved. But when it moved, if you can somehow change the stator magnet position in the next position, so rotor has to move further, and then you do it similarly. So this is basically using magnetic property, creating a torque. So you can see, and I hope you understand easily that the rotor will move. That means you've created a rotational movement. That is nothing but torque. Now you can ask the question, stator is stationary. How do you create a rotational magnet? So that is the importance of electromagnet. Now, what is electromagnet? You are creating a magnet by applying electricity. For example, almost all of you study solenoid, right? So what we used to do, there is a piece of some magnetic material, and let's say if I send some current I, right, it will create a magnet, right? So typically we use, remember this kind of rules. So if your right hand finger curls to the current, this thumb will show direction of the flux, right? So if this is my direction of current, this will be the direction of flux, and generally from N pole flux will come out, S pole it will go back. So this is an example of electromagnet, isn't it? So if I give current, then only it will become magnet. What if I stop current? It won't be magnet anymore, right? In simple terms, isn't it? I hope you're getting the point. So if I have multiple coils across multiple segments of the stator, and if I excite them as per my wish, I can create a magnetic field in the stator which will change its position. Isn't it amazing? So what I'm trying to say is very simple. If I have a coil here, if I have a coil there, if I have a coil here, if I have a coil here, imaginary, just think about it. If I excite this coil, let's say I create an NS pole like this, isn't it? So if I have a rotor like this, it will move. After this, I disconnect the current, I provide current in this coil, right? Again, I create something like this. So this will rotate. So that is the beauty of creating a torque through electromagnetic arrangement, right? So in the stator, we are exciting some coils as per our choice. Now, you can ask a question, so how do you decide which coil to excite? For that, see, when the rotor is in this earlier position, this Sn, okay, let's say I want to have this direction. This is what? Counterclockwise, right? We call it anti-clockwise. So when I want to move this coil this way, am I going to, let me give number of the coils. Let's say this is 1, 2, 3, 4, 5, 6, 7, just an example, right? So I want to excite the coil, I have to rotate the rotor in anti-clockwise. So which coil I'm going to excite? Is it coil number 1 or coil number 3? Given an option, which one you're going to do? Say option is coil 1 and 5 together, that can be one of the options, and coil 3 and 6 together, or only 3, only 6. So logically, you will, most probably you will agree that I can excite coil 1, I can also excite coil 5. For example, if I create S here and here, it will create a rotation. But if I create something here, N and S, it is kind of a 90 degree to this rotor, right? So it won't make much impact. In fact, it can create problems. So what I'm trying to convey is very clear. To know which coil to excite, I must know in which direction I need to move. At the same time, where is my rotor position? I hope you agree. I repeat again slowly. To understand which coil to excite, I must know where is my rotor and which direction I need to move, right? For example, if here is my rotor and S, there is a coil here and there is a coil here, and I want to rotate it like this. So it makes more sense to create S here and here, right? It will rotate like this instead of creating an N and S here. It won't create much impact because sometimes it will repel, sometimes it will attract, and it can nullify sometimes, right? So generally, quadrature or 90-degree business is not at this point. Just for an example, right? Similarly, if I wanted to rotate in the opposite direction, so then it makes more sense to create N here, S here. It will create more repulsion, right? So just for visual, for simplicity, I hope you understood that I need to know where is the rotor. In other words, where is the magnet on the rotor, right? And which direction I need to move. So which direction I need to move generally comes from your driver. The driver, when he or she pressed forward or reverse switch, that's how you give signal to the motor controller, which direction to move, right? And then rotor position information, for that position sensors are used, okay? Those Hall sensor, that resolver, what do? They are strategically placed on the stator to tell you the rotor position, okay? And then with this, you understand which coil to excite, which not. And what in what sequence. After this, which coil to excite. After that, what to do. So all these things generally will come. So similar BLDC, will see generally we just follow a truth table, a sequence. Based on Hall signals, you can decide which switch to turn on, which phase to give current and all. So that's about electromagnetic torque. So what we simply do, using the motor controller, we excite or we give current to the coils as per our wish based on the rotor position and direction information. Okay, that's how we create torque. So this torque, whatever is created, it is basically proportional to the current in the stator and then magnetic strength on the rotor. Okay, so basically, if you remember, when you have two magnets, the relative attraction and repulsion, that depends on the magnetic strengths, right? Magnet strength and the angle between them. So how can I make magnet stronger? I use rare earth magnet or very strong magnets, right? Stronger the magnetic field, more torque you can generate. Similarly, electromagnet, how can you make it stronger? You have to pass more current, more number of turns, right? So these things are you have to provide. But then of course there is a physical limitation of how many currents you have to pass. As I told, the thickness of the copper winding. If you send more current, thickness of the copper has to go more, and then you can't have multiple turns, right? Because size of the motor has to be limited. So within the limited size, you have to fit, let's say, n number of turns, and then some current also has to be sent in those coils, right? So due to physical limitations, there is always a limitation on how much current you can send, how many turns you can have, thickness of each of the copper wires. So based on those limitations, your torque of the motor will also get limited, right? How much strong magnet you can keep on the rotor, what is the size of the magnet. So those will decide your finally torque capability of the machine. I hope this point is clear. So in PMSM induction machine, right? Like this, for example, mostly in PMSM induction machine also, what we do in the way we give power supply to the machine, we give three-phase AC that I told multiple times. So the way we give three-phase AC supply to the machine and the way we do the winding in the stator, two things are simultaneously important. The way we give current to the machine and the way we do the windings, it creates in the stator, it's created a rotating magnetic field. Okay, this I'm going to discuss tomorrow. Today almost time is up. So the way we control the motor controller, right? We don't give fixed AC supply, we give variable AC supply, right? So using motor controller, so we create a rotating magnetic field. So in effect, the magnetic field rotates, and as a result, the stator, it is a magnet, it will also rotate simultaneously. So that is how a machine like PMSM, induction machine, and some of BLDC also similar, not exactly similar, concept-wise same, but the stator of PMSM, induction machine, your synchronous reluctance motor, these all have similar principle. Okay, so I hope you understand about electromagnetic torque, right? So it depends on what is your rotor magnet strength, how many number of turns that there in your stator, and how much current you are sending in the stator, right? Another concept was reluctance torque. Let me complete that, and then I can take up some questions. Okay. Now, what is reluctance? So basically, in electric circuit, when we apply some voltage, and if I apply voltage to some load, let's say we talk about DC voltage. Okay. So load will have some resistance, isn't it? So the current that flows in the circuit, how we decide? Current is nothing but voltage by resistance, isn't it? So in electric circuit, resistance is something which opposes flow of current. Okay. What is resistance? It is a property of material by virtue of which it opposes flow of current. So current is given by voltage by resistance in electric circuit. In magnetic circuit, this, for example, when we create electromagnet, it produces flux. Right. So whatever current we are sending through some supply, and let's say number of turns is n. So this in electrical engineering call it EMF, like, right? Remember the generator will produce EMF. Similarly, in magnetic circuit, we say this number of turns and that current Ni, that is creates something called MMF, magnetomotive force, and that produces a flux. And something that opposes flux is the reluctance. Okay. I repeat. To the electrical analogy in magnetic circuit, in electric circuit we produce electromotive force. In magnetic circuit, we produce magnetomotive force, which is proportional to current into number of turns. Right? In electromagnet, what we do, we send some current into some number of turns, isn't it? So that product of N into I, it basically creates that magnetic field. So we equivalently call it magnetomotive force. Magnetomotive force. Okay. So this magnetomotive force basically produces flux. Like in electric circuit, the EMF produces current. And who opposes current? The resistance. In magnetic circuit, who opposes flux? It is reluctance. So basically, reluctance is property of material by virtue of which it opposes flux flowing through the material, right? For example, if I have air as the medium, air has much higher reluctance than iron. Okay. So for simplicity, let me explain. If I have this magnet, N pole, S pole, let's say it is producing 10 flux. Okay, and it has to come back here. From N pole, it will come back to S pole. Now, yeah, just 5 more minutes and we are going to wind up. Those who have some questions, I'll give you mic access so that we can discuss. Okay, please keep your questions. So, now let's say, theoretically think about it. We have an N pole here, and let's say we have an S pole here. So, flux will go like this. Okay. Now, this is air medium. Now, alternatively, if I had this arrangement, think about it, N, S, and I had created a path like this using some, let's say, iron or steel. Now, what do you think? In which way the flux will move? Option 1, it will go like this. Option 2, it will go like this. So like in electric circuit, current always flows through least resistance path, right? That I think you already know. Current tries to flow through least resistance path. Similarly, flux will try to flow through least reluctance path. Whereas the opposition is minimum, it will try to flow there, right? So now think about it. Here option 1, it is going through air. Option 2, it was going through iron. So in which path reluctance will be less? So you will see reluctance of iron is much lesser than air. Okay. So naturally, the flux line will try to pass through the through this iron path. Okay. Now we can say it is analogically it's okay, but what do we understand from this? So here is the beauty of motors like switched reluctance motor and synchronous reluctance motor. Okay, how? I'll show you. Just give me a minute. I'll get some image. Yeah, I hope this will be. So I hope you understood the reluctance. Now this flux has kind of a rubber band feature, elasticity. So you must have seen that if you stretch rubber, right, it always tries to come to its original position, isn't it? So basically it creates tension and stress, whatever you in your terminology. If you stretch them, it always tries to go back to the state or its original position, right? So similarly, look into this structure. Let me make it slightly bigger. This is not much required. So what I'm showing now is basically kind of SRM. What is SRM? Switched reluctance motor, which based on reluctance principle. So in switched reluctance motor, this internal part, right, this is rotor, and the outer side is of course stator. So rotor is made of some steel material, no magnet. Okay, and stator is having electromagnet. Basically there is no permanent magnet, but then effectively we are creating electromagnet. So here you can see for this arrangement, if I excite coil A, so coil A current goes like this, and then through this back side it comes back. So let's say we send some current through this path. So there will be a magnetic arrangement created in this part, isn't it? So let's say due to this current direction and all, let me try to do a simplified version of this. So let's say we have created a N pole here and an S pole here. Okay, and your rotor equivalent structure is like this. Okay, you see, I hope. So it is not permanent magnet in the rotor. It is still some steel or iron material. So as a result, your flux will try to flow this path because it will see less reluctance as compared to that other part where you see more air. Right? If it follows the shortest route, it is going to see more air. But if it follows this route, it will see less air and overall less reluctance. But in that process, basically it gets stressed. The flux line, it gets stressed. So it will try to rotate this rotating arrangement if it can to align along this, where it will get its comfort zone and least reluctance path. So that is how it creates reluctance torque. Basically, with this previous arrangement, the flux line gets stressed, okay, and it tries to come back to its natural position, right, relax. So in that, to achieve that, it tries to pulls the rotor where it goes in the natural shortest distance and natural occurrence position. So in that way, it creates a reluctance torque. So basically, it saw variable reluctance, right? In one path, high reluctance, one path, less reluctance. So it tried to flow through the less reluctance, and in the route, it also tried to rotate the rotor so that it goes to least reluctance, at the same time, least direction, distance, right? So that is how it creates a reluctance torque. And then once it gets aligned to that particular coil, right, we are going to excite the next coil, which I don't know whether I have showed it. So for example, what will happen next? It will align to this. By the time this coil will go there, right, this segment. So then we are going to excite this coil so that it goes like this. And this keeps on happening like the Duncan carrot business. So very simple. The rotor structure is designed such a way that we call this arrangement tooths. So you can see number of poles, so number of stator poles and number of rotor poles, they are not going to be equal. So at any point of time, some poles will be aligned, some poles will be non-aligned. That is the beauty of the design. So those who are not aligned, we will try to align them by exciting proper relevant coil in the stator. And once they have become aligned, you see some other pole, they will become non-aligned. Okay. For example, you see in here, this is more or less aligned. So I'm not going to excite that B coil, no excitement, right? But I'm going to excite the other coil where it is not aligned. But you must realize that once these get aligned, some other pole, it will create non-alignment. And that coil we're going to excite. Okay. But again, you need to know what is the rotor position, right? To know which coil to excite. So So here there is no magnet used, no permanent magnet used, right? So what is the benefit? Cost will be on the lower side. Generally these are very rugged because there is only steel material, right? No glue, no additional attachment and all, right? So these are very rugged. It needs less maintenance. It is low cost because no high cost magnets are used. But then problem is that their size for same torque rating is typically higher than PMS and BLDC. See, PMS and BLDC, there is a very strong magnet, right? That's why their size is much lesser. But here, it has to rely on the reluctance torque, which is not as strong as your electromagnet-based system typically. Okay, so as a result, what happens is that these motors, even though they're very rugged, generally on the lower cost, but their size weight becomes more for same torque, same power rating. Okay? So, without going into much detail, remember there are two reluctance-based motor. One is SRM. What is SRM? Switched reluctance motor, the one we discussed, this one. Okay, and there is another called SYRM, synchronous reluctance motor. So it also based on reluctance principle. Okay, how? So this is the example. Okay, so here you can see the flux can have two parts. One is like this, right, from stator to rotor. See, it goes to the steel, steel, and only very small area. So mostly it will have low reluctance. I hope you are getting the idea. Because it is mostly going to the steel material, right? Very low reluctance. And then, take another route. Look at this route. So there you have some air. These are all cut out sections, right? These are what? Air. Basically, they're from steel material you've taken out. So these are nothing but air. So it will have high reluctance. I hope you're getting the idea, right? So basically what you have created here, in two different directions, if flux, if force, it will see different reluctance. So naturally it will try to go through the least reluctance path, and that's how it will create the torque, okay? To improve this performance, torque, etc., in synchronous reluctance motor, sometimes what is done is, that will take a suitable color, I don't know whether you can see, during these segments, some magnets are kept, added. So in those air cutout sections, additional magnets are inserted to improve performance, right? Then they're called PMA SYRM. SYRM is synchronous reluctance motor. PM becomes permanent magnet assisted, okay, synchronous reluctance machine. So this is one of the quite interesting machine that a lot of research is still going on. In fact, if I understand correctly, Tesla's recent vehicles, they're using this machine with permanent magnet. Okay, so their benefit is that they utilize both electromagnetic torque as well as reluctance torque, right? And generally they have a more rugged structure, and they can give similar performance to PMS with lesser magnet. That is the more benefit. So as a result, if you design them properly, cost may be reduced, dependency on foreign supply that goes down, but it has some drawback, especially in these ridge structures. So you have to make them very thin for better performance, and that creates some mechanical strength and manufacturability issues. So that is still a lot of, again, I'm saying a lot of research is going on to improve the performance in these machines. So quick summary, just give me 2-3 minutes and then we're going to wind up on this. See, a lot of topics, again I'm saying, I discussed, I'm going to wind up in 2-3 minutes. A lot of contents, I did not go line by line in the interpreted document, but if you go through this document, you will realize that I have covered several things, and some things we'll discuss tomorrow. And then what tomorrow main thing we're going to do is, this PDF has become non-responsive. Tomorrow we're going to take a comparison of different motors so that you understand which motor is good for EV, right? Of course, we know PMSM is better, then why that kind of small comparative statement. And then we're going to take some calculations, right? For example, for a particular vehicle or for some things, how do basic calculation on how do we select motor ratings and all. Some idea we're going to get in tomorrow's class. So with this, let me wind up for today. Somehow this PDF has become non-responsive. I hope it will be all right. If you have any question, please type it in the chat box, and also